3D vectors. Until now you've looked at vectors in 2 dimensions with x and y, but in reality we're more likely to use 3-dimensional vectors which represent things moving in space in the real world. It's difficult to draw 3D objects in a 2D piece of paper, but there's 2 common ways to do this. Represent it in a grid with x and y and z, x along, y back, and z is up. Sometimes this is drawn in textbooks with the x-axis coming slightly forward, the y back, and the z up. So neither is ideal, you have to imagine where things go. And you can represent a vector A coming from the origin, like this. Sometimes we use unit vectors to represent 3D vectors. There are 3 unit vectors, I, j, and k. Now a unit vector has length 1. So the I unit vector represents a vector with length 1 in the x direction, 1, 0, 0. This is the x direction. Unit vector j represents a vector with length 1 in the y direction, 0, 1, 0, y direction. And k is a unit vector in the z direction, 0, 0, 1. Drawn on the axes, x, y, z. These are the unit vectors. This can be I, j, and k. Remember to draw arrows on your vectors. Forgot the x-axis there. So this is helpful because you can represent vectors using I, j, and k instead of the components. If we take, for example, the vector u, which we've been writing as 3, -4, 5 in a vertical bracket, we can write this as 3i, because it's length 3 in the x direction, subtract 4j, because it goes 4 in the negative j direction, and plus 5k, because it goes 5 units in the z direction. So there's 2 ways to write the same thing. 2 options or 2 forms for 3D vectors. So this vector u would go 3 along, 4 back, and 5 up. Maybe something like this. Vector u. It's difficult to see that in a 3D picture. (3D vectors). There is good news. Because most of the rules in 2D apply. Most of the rules for 2D vectors apply to 3D vectors as well. For example, adding vectors, u plus v. We have 3D vectors 3, 5, -2, and we would like to add vector v, negative 2, 3, 6. We did this in 2D just by adding up the x, y components. Now we add up the x, y and z components. 3 add negative 2 is 1, 5 add 3 is 8, and negative 2 add 6 is 4. So it's just an extra component to add up. That's all. We can also find the magnitude. If u is 2, negative 1, 5, the magnitude of u we write with vertical brackets. U, magnitude of u. In 2D, we did x squared plus y squared inside the square root. It's like Pythagoras. This is like 3D Pythagoras. And we do x squared plus y squared plus z squared. So just remember to square all three components this time. 2 squared plus negative 1 squared plus 5 squared. So we have the square root of 4 plus 1 plus 25. Square root 30. Subtracting vectors. If we have u, subtract v. Vector u is 4, negative 5, 1. And vector v, 2, 3, negative 4. We can subtract these. 4, negative 5, 1. Subtract 2, 3, negative 4. Just subtract each component. The x components, 4 subtract 2 is 2. The y component, negative 5 subtract 3 is negative 8. And the z component, 1 subtract negative 4 is 5. So it's the same rules as 2D vectors, just do it for the z component as well. Multiplication by a scalar. We have u, 5, 3, negative 2. And we would like to find 5u, so we're just multiplying by the scalar number 5. We can do this. Just multiply each component by 5. 5, 3, negative 2. 5 5s is 25, 5 3s is 15, and 5 times negative 2 is negative 10. Now don't forget to complete this with the brackets. Showing that vectors are parallel in 3D is the same as in 2D. This time we're given two vectors, 2i plus 6j subtract 4k, and v is 3i plus 9j subtract 6k. So these are written in IJK notation. We can change them back into the column form. 2, 6, negative 4 are the components, and v equals 3, 9, negative 6. So looking at them like that, we can see there's a connection between these numbers, 2 and 3, 6 and 9, negative 4 and negative 6. So looking at u, we can see that just multiply by 1.5 to get v, because 2 times 1.5 is 3. Or we could see it like 3 u's, 3 of u's is equal to 2 v's, because 3 2's, 3 times 2 is 6, and 2 times 3 is also 6. The y components works this way too. 3 6's is 18, and 2 9's is 18 as well. The z components, 3 times negative 4 is negative 12, and 2 times negative 6 is -12, so I'm sure that these are parallel. I just have to write it down now. So 3u equals 2v. That's the property. There are some alternatives. We could write u equals 2/3 of v, or we could write down that v equals 1.5u in a decimal, or v equals 3/2u. Any of these shows that they're parallel. Use one of these properties and say, therefore, u parallel to v. Position vectors in 3D. If we have A as the coordinate 3, -2, -7, and B is the point 5, -4, 2, we can find AB. We did this in 2 dimensions using B subtract A. We can still do this in 3D. 5, -4, 2, that's the vector B. Vector A is 3, -2, -7. Just a matter of subtracting. 5 subtract 3 is 2. -4 subtract -2 means -4 add 2 takes us to -2. And 2 subtract -7 does 2 add 7, 9. So this is the same process as for 2D vectors. Collinear vectors, or collinearity, is also the same as 2D. So if we're going to prove that A, 2, -3, 5, B, 9, -6, 9, and C, 23, -12, 17. If we're going to show that these are collinear, we can work out AB, position vector, B minus A, 9, -6, 9, minus A, 2, -3, 5. 9 subtract 2 is 7, -6 subtract -3 is -6 add 3, -3, and 9 subtract 5 is 4. That's AB. Now find BC. BC is C minus B, 23, -12, 17, minus 9, -6, 9. 23 subtract 9 is 14. -12 subtract -6 is -12 add 6. That's -6. And 17 subtract 9 is 8. Here are 2 vectors. You can see there's a connection between the 2 of them. It's 7, 14, that's just doubling, doubling, doubling. So that means that 2 of the vector AB is equal to BC. So 2 of the small ones is equal to the large one. 2 small ABs equals the large BC. Or if you preferred, you could write AB is equal to half BC. Write either of these. So then you say, therefore, put 3 dots for therefore AB is parallel to BC, and B is a common point. So they're not only parallel, they're actually in a straight line connected by B, the common point. AB is parallel to BC and B is a common point, so ABC are collinear. Exactly the same as in 2D.